Welcome to AI Research Roundup. I'm your host, Alex. Today is May 8th, 2025, and we're diving into an ICLR conference paper, Control-Adapter, an efficient and versatile framework for adapting diverse controls to any diffusion model, published just over 3 months ago. This paper proposes an efficient way to use existing ControlNets, which are tools that add specific guidance to AI image generation with almost any diffusion model. Diffusion models, you'll recall, create images by learning to reverse a noise process. The issue is that adapting these ControlNets to different diffusion model backbones, or main structures, is computationally heavy. So Control-Adapter uses lightweight adapter layers to bridge this gap efficiently. Alright, so this first figure really sets the stage. It shows a diagram of the Control-Adapter in action. You can see various input conditions on the left, things like depth maps, which tell the AI about distances in a scene or human poses, and even canny edge maps, which are like detailed outlines of objects. These conditions go into a small, pre-existing image control net, which is kept, quote, frozen, meaning its parameters aren't changed. Then, the Control-Adapter, the new part, links this to a larger diffusion model, also frozen, to produce the final controlled image or video, shown on the right. Building on that architecture, these next two graphs really highlight the efficiency. On the left, for video, optical flow error, measuring motion accuracy, so lower is better, is plotted against training GPU hours, a measure of computational effort. Control-Adapter, the orange line, quickly achieves low error. On the right, for images, SSIM, or Structural Similarity Index measure, a score for image quality where higher is better, is shown. This Structural Similarity Index measure also improves rapidly. This efficiency is striking. Control-Adapter performs strongly in under 10 training GPU hours, while some baselines needed 700. Okay, so looking closer at the mechanics, this figure details the Control-Adapter's architecture. On one side, you have a pre-trained image control net, and on the other, the main diffusion model. Both of these are kept frozen, meaning their core settings aren't changed. The Control-Adapter itself, shown in orange, sits in between. It's a set of lightweight, trainable layers that bridge the feature gap. These include specialized convolution layers, which are mathematical operations that help the model identify features like edges or textures in the data, and attention mechanisms that let the model weigh the importance of different input parts, like spatial areas or temporal moments. This lean design is what enables that impressive efficiency. So building on that lean design, this figure shows how Control-Adapter handles multiple control signals at once, especially for video. You see several frozen control nets on the left. Their inputs combined by the Control-Adapter before going into a frozen video UNet, a network structure often used for video tasks. The right side details 3 ways they designed a mixture of experts, or MOE, router. A mixture of experts system is like a smart switchboard, combining different expert inputs. They tested various router designs, some using multi-layer perceptrons, or MLPs, which are simple neural network layers, or even Q-formers, a type of attention module, to manage these combined controls effectively. Alright, so we've seen how Control-Adapter can manage those combined controls, and this table now gives us a quantitative look at its performance for generating images with a single control condition. It uses metrics like Fréchet inception distance, or FID. This is a score where lower values mean the generated images are more realistic and diverse. Another one is the Structural Similarity Index measure, or SSIM. Here, higher scores indicate better image quality. Notice how Control-Adapter consistently performs very well across different diffusion model backbones and control types, often achieving top results, which really backs up its efficiency. Okay, so that was image generation, and now this table shifts focus to video generation, specifically with a single control condition, evaluated on the Davis 2017 dataset. We're looking at Fréchet inception distance again, and also optical flow error, both where lower scores are better. Across various video model backbones, like Hotshot XL or Latte, which is a diffusion transformer or DIT-based model, the Control-Adapter, paired with an SDV 1.5 control net, consistently achieves excellent, often top-tier, results for both depth map and canny edge controls. This strong performance really underscores its versatility for video. So after seeing those strong video results, this table gives a broader overview of capabilities supported by different controllable image and video generation methods. You can see various features listed, like image control, video control, handling sparse frames, which means working with videos where you only have a few keyframes as guidance, multi-condition control, and compatibility with different model backbones. What's really striking is that Ctrl-Adapter, listed as Rs, is the only one here with a checkmark in every single category, really highlighting its comprehensive versatility compared to other approaches. So considering that impressive versatility across the board, the main takeaway here is really the efficiency. Ctrl-Adapter slashes the training time needed, making advanced control much more accessible. And it does this while maintaining or even exceeding the performance of existing methods across a wide range of tasks, from images to videos, and even adapting to different underlying model architectures like UNets or those diffusion transformer-based models. Well, that's all the time we have for this AI Research Roundup. Thanks for tuning in, and we'll catch you next time.